the introduction. So the UNSW Chemical Society proudly presents today a talk by Dr. Mitch Schulte from NASA, where he's going to talk about the 2020 Mars rover that was recently launched back in the end of July. So anyway, in case you don't know, the Chemical Society is a group of us here at the School of Chemistry, and the mission of the Chemical Society is to promote chemistry in general. And so I think a lot of the instruments on board the rover are chemically related, so we're going to learn some more about that today from Dr. Schulte. So a little bit more about Dr. Mitch Schulte. He got his bachelor's and PhD in Earth and Planetary Sciences from Washington University in St. Louis, Missouri, in the US. And he's a program scientist with the NASA Mars Exploration Program. He's a program scientist with the Planetary Science Division in the Science Mission Directorate at NASA headquarters in Washington, D.C. He's a lead scientist for the Mars Data Analysis and Habitable Worlds Program for the Mars Exploration Program and Planetary Science Division. And he also happens to be a senior editor of the scientific journal Astrobiology, which many of you may be familiar with, and serves on the Interagency Working Group on Ocean Exploration, is a part of the U.S. Advisory Committee for Scientific Ocean Drilling. And he's also part of the board of the Big Questions Institute here at UNSW Sydney, where they discuss and put on public lectures about origins of life type of questions. So it's really exciting to have Mitch here with us today, at least just over Zoom. And so with that said, Mitch is going to tell us a little bit more about the Mars 2020 rover mission. So please take it away.
Thank you, Albert, and thank you, Anna, and thank you to the Chemical Society at the University of New South Wales for the invitation to speak. I'm very excited about the mission, and so I'm really happy to get the opportunity to talk to you about this. So, Albert, can you give me a video check here and make sure you can see my slide?
Oh, it's all good on my end. Yep.
Okay, fantastic. So what I do want to do is, again, thank everybody for attending on a Friday afternoon. Hopefully everyone is healthy and well there, dialing in, and that it continues to stay that way. And as you guys are in spring now, I hope the weather is warming up and you guys are having a nice time. So I do want to go through a little bit about a background about why we need to keep sending these missions to Mars. A lot of you may know that we have been sending missions to Mars for about 50 years, a little over 50 years from NASA. We started with flybys, then figured out how to put things into orbit, getting much more clear picture of Mars as we went each time. We finally landed things on the surface back in the 1970s with the Viking missions. We've had our successes and failures, and I'd be happy to come back sometime and talk about the history of Mars exploration. But for now, I want to focus on where we are and what we're planning to do from here on out on Mars. So, as you all may know, Mars today, of course, is a very cold desert. This is a photo taken by the Curiosity rover of an area in Gale Crater called Dingo Gap. You can see Mount Sharp there in the foreground, and that's where Curiosity is now, studying the sedimentary layers that make up Mount Sharp in the center here of Gale Crater. So what we're interested in finding out when we send these missions is a variety of things. So we first started trying to figure out, just to get a better general picture of what Mars is like, and try to understand its geology, its geological history through time. So as I mentioned, today it's a very cold desert, but as we've been sending these missions to Mars over time, we've learned enough to convince the scientific community that despite the fact that modern Mars is a cold, dry, dusty desert, a very long time ago in Mars's history, it was a very different place and had liquid water at the surface, may have had processes that might have led to life getting established on Mars, So this is an artist's rendition on the right-hand side of what Mars may have looked like about 3.5 billion years ago. Now, as you may know, the only real way to figure out what has happened in the history of a planet is to look at its rock record. And so this is one of the things that we're interested in doing. So 3.5 billion year old rocks on Earth are actually relatively rare. And the reason for that is because Earth, of course, has plate tectonics, where the lithospheric plates that make up the outer surface of the Earth shift around through time as the Earth is trying to get rid of its interior heat. Through that process, a lot of the old rocks get destroyed because they get recycled, they get shoved back down into the mantle where they remelt and then erupt as new volcanic rocks. So there are very few areas on Earth that actually have really old rocks. And of course, some of them are here in Australia. And we'll talk a little bit more about a couple of these locations in just a little bit. But as you can see, the surface of Earth doesn't really have a lot of really old rocks on them. But looking through the rock record and going back to more and more ancient rocks on Earth tells us a lot about what has happened to the planet. So we're very interested in doing the same sort of thing with Mars. Now, it's very difficult to do that from hundreds of millions of miles away. Once we figured out how to send rovers to the surface where they can drive around and not just stay in one place and look at things up close rather than just seeing them from orbit, we're starting to get a little bit better picture of what Mars was like through its past. It turns out that about 50% of Mars's surface is older than about 3.5 billion years old. As I said, these kinds of rocks are fairly rare on Earth, but on Mars, a lot of the surface is really old. And so by studying a lot of Mars's surface, we'll be able to understand its history and what it looked like 3.5 billion years ago, and try to determine what the rock record tells us about the potential for life to have started on Mars. So this is a quick snapshot of what the biological timeline looks like here on Earth. So throughout most of Earth's history, life existed as single-celled microorganisms. So they would grow together and make structures, and we'll talk about that in just a second. But we don't see the development of multicellular animals or multicellular organisms on Earth until around 1.2 billion up through about 600 million years ago. And of course, you guys in Australia have the Ediacaran fauna there in South Australia that contains some of this earliest record of multicellular kinds of organisms on Earth. So again, we get this picture from 600 million years ago that there are these organisms that started to develop multicellularity, and that gives us an important snapshot of what has been happening with life through time. But before that, so for 3 billion years before that, life existed primarily as single-celled microorganisms. And in fact, it's true that life today, most life on Earth today, is stuff that you cannot see with your naked eye. So we get focused on looking at dinosaur fossils and fish and sharks and insects and all that kind of stuff. But the real drivers of biological function on Earth are primarily microorganisms. It was true when life first started here on Earth, and it's true today. So because the nature of life in the rock record on Earth, where we're trying to look for really old rocks, would have been single-celled microorganisms, we're very interested in trying to figure out what it is that we should be looking for. So again, classic fossils you see here on the left, fish and plants and all that kind of stuff. Those multicellular organisms or animals or plants, they're less than about 650 million years old. So that doesn't really tell us what was going on a very, very long time ago. Again, because microorganisms would have made up the life on Earth before about 650 million years ago, we need to figure out what the nature of microbial biosignatures is. So up to about 3.5 billion years ago, the picture on the right shows you what those rock records would look like here on Earth. So these are, of course, akin to modern day stromatolites. So again, Western Australia is a great place to find these. If you go out to Shark Bay, you can see these things for yourself. So these are mound structures. We refer to them as microbial mats. And what happens is that these communities of microorganisms live together, and they sort of, they live symbiotically with each other. They build up these big mounds as they trap sediment. And then because there's a significant component of photosynthesis in these stromatolites in Shark Bay, they build up these big mounds as they try and get above the sediment so that they can have access to either light or nutrients or water. And so through time, they build up these structures. Now, when we look at ancient rocks, what we often see are very similar kinds of structures. So we find in the Pilbara region, which is not too far away from where Shark Bay is, we find 3.5 billion year old stromatolites. Now, what do these look like? Well, they sort of look like this. So as you can see, they look very similar to what we were just looking at from Shark Bay. If you were to cut them in half and look at them on the side, you see these layers that get built up over time as these microorganisms lived and trapped sediment, and they would grow up into these mounds and they make these structures. These are the kinds of structures that can get preserved in the rock record for us to look at. So the organic matter, of course, either gets eaten by something else or it degrades through time. And so we don't often see a very big signature of organic matter, although some of it does get trapped, and we'll talk about that in just a minute. But primarily what we see are these structures in the rock record that give us this clue that this structure was created by life. So again, this is an example of a really old, ancient record of life here on Earth, and these are found out in the Pilbara region in Western Australia. Now, how might we find ancient, possibly non-Earth-like life, right? So if it's very difficult to convince the scientific community when you're looking at these features in Western Australia that, yes, 3.5 billion years ago, there was something living here, and this is the record, this is the deposit that this life made, because it's a very difficult, it's a high bar to convince people that what you're seeing is actually evidence of life, because there are often non-biological explanations for seeing a lot of different things. And so there's a variety of different kinds of information that you can tease out of the rocks to help convince you that when taken together, this is evidence for life. So we've talked about the physical and chemical structures already. So the pictures on the top right here are ancient stromatolites. Again, the ones at the bottom on the right are the Shark Bay modern ones. So we see those physical and chemical structures, but of course there are a lot of geologic processes that make things that could fool you, fool the eye and make you think that it's something that it's not. So what we're interested in is adding to the information set that we collect from rocks that are really, really old to try and help convince us that these are potentially biosignatures or evidence in the rock record of life. We often use carbon isotopes. So as many of you may know, organisms are inherently lazy. So when given the choice between taking a carbon-12 or a carbon-13, we'll generally take the lighter carbon just because it's easier. It takes less energy to incorporate that into your cellular structures. And so we often see molecularly light carbon or hydrogen incorporated into organic matter that is created biologically relative to non-biological processes. So if we see any organic matter in the rock record, we can study the isotopes to give us some indication that maybe biology was involved in fractionating those isotopes. Again, I mentioned organic molecules themselves. There are particular structures of organic compounds. For the organic chemists in the audience, you guys all know this, that are very difficult to explain through just chemical processes or geochemical processes. And so there are particular structures that organisms like to make, for example, their cell walls, or the enzymes or the proteins or things like that. And so if you found evidence of those kinds of things that might be difficult to explain through non-biological processes, those might be indicators of biological activity. There are also sets of minerals that biology likes to precipitate. This is an example of magnetite, which is an iron oxide mineral that's magnetic, that particular types of bacteria precipitate inside their cell walls. So again, the ordering, the structure, the arrangement of these particular minerals it can be indicative of biological activity. So all of that is to say that we are sending this next rover to Mars, the Perseverance rover, as it is now named, to look for evidence that life might have left behind in 3.5 billion-year-old rocks on the surface of Mars of its presence. So the mission overall has four main objectives. The first is geologic exploration. So anytime you go out into the field, if you're a geologist, the first thing you want to do is case the joint. You want to understand where you are, what sorts of geologic processes led to the rocks that you see, what kinds of environments created the particular rocks that you see in your field area. So we want to explore an ancient environment on Mars, understand processes of formation and alteration of that rock record. The second mission objective, of course, as I mentioned, is habitability and biosignatures. So we want to understand whether the landing site, which I'll talk about later on during the talk, was a place where microorganisms could have lived if life had ever arisen on Mars. So that's the habitability component. So we want to assess whether this was a place life could have existed. We want to look in the rock record for evidence of past life. So all those great features that I was just talking about, textures and mineralogy and all that other kind of stuff. And we want to select locations as we're going around the site, because we of course have a rover, so we can drive from one place to another. We're going to be looking for sampling locations that we think the environments have created high biosignature preservation potential. So as a lot of you know, part of the reason that these microfossils are so rare on Earth is because it is very difficult to preserve those structures, especially again, as we're talking about single-celled microorganisms that didn't make hard parts, they didn't make bones or anything like scales, anything like that. It was all organic. And so preserving that material, either the organic material or the structures that get made, is actually very, very difficult. And so one of the important things we want to think about is where are the places where it's most likely that these would have been preserved. Now, of course, it's much more difficult here on Earth because of plate tectonics and making sure that those get preserved. But it's generally not easy. And on Mars, it might be a little easier, but we just want to make sure that we're essentially looking in the right places. The third major objective of the mission is to prepare what we call a returnable cache. So the rover will have a set of sample tubes. It will have a coring drill on the end. And so the sample tubes will be put into the coring drill, and we'll be able to take samples of the surface of Mars and collect them and seal them inside these tubes. So we'll have on the order of 40 samples. We'll also want to make sure we take blanks to check for contamination that we may have brought with us from Earth. So we can subtract that out and make sure that what we're looking at is actually Martian in nature. We want to make sure we get a variety of rocks because we want to be able to date the samples. We want to make sure that we understand the age. We want to get a variety of sedimentary rocks. We want to get a variety of rocks that might contain different kinds of information that will help us better understand the area. The idea, and I'll talk a little bit about this later on during the talk, is that we're going to leave these samples on Mars. Mars 2020 will be collecting the samples, and we are currently working on plans to go retrieve those samples, the sample tubes, off the surface of Mars and bring them back here to Earth so that we can study them in laboratories here. Our final objective is to help prepare for human exploration of Mars. Of course, this is one of the great goals of mankind now, is to finally get people all the way out to Mars. And so every time we send a spacecraft to Mars, gives us a little bit more information that hopefully will help make it a little easier when humans get there. In particular, this time we have a couple of features on the rover, a couple of instruments that will help us get a lot more information that will be relevant to human exploration. I'll talk about these a little bit later on, but primarily one is a weather station, and then the other one is going to help us demonstrate in situ resource utilization, or ISRU. So let's go a little bit over the mission overview here. So launch, many of you may have watched the launch, and if you did, I hope you did. It was pretty spectacular. I watched it online like you guys did because of the pandemic. Some of us were not allowed to travel down for the launch, but the team worked very hard to get it off on time. It left the pad, as you can see in this picture here, on July 30th. It will have a 7-month cruise to Mars, arriving in February of 2021. We'll talk about entry, descent, and landing and the surface mission as we go along here, but I have a couple of pictures of the spacecraft getting ready here to be put into the rocket. So this is down at Cape Canaveral in Florida. So the picture on the top left is the rover, all fully assembled with some protective foil and stuff on the wheels here, and it's undergoing some environmental tests. So this is a picture of the rover right before it was put into the capsule. So this is called the fairing. So that's the nose cone of the rocket, which protects the rover as it travels to Mars. The picture in the middle at the bottom here is as they were stacking the spacecraft, we call that, which is putting all of the pieces together. So I like this picture because it shows you at the top here is the cruise stage. This round gold thing here is a propellant tank that helps spin the spacecraft because it travels, it slowly spins, and to do any course corrections that we'll talk about in just a second as well. The second part here is this, which is the back shell, which helps protect the rover. It also has these ports on it, these little round holes. Well, they're not too small, but these round holes here, these are help us guide the rover as it's coming in through the atmosphere of Mars to get it to the exact right place. Tucked in underneath that, you see the rover here all folded up. And then on the bottom is the heat shield. So of course, Mars does have an atmosphere. It's very thin, but it's enough that we have to deal with it. And in order to do that, we actually have to have a heat shield because as the spacecraft enters the atmosphere of Mars, it starts to heat up due to friction with the atmosphere. Now, if any of you sent your name in to go to Mars on the Mars 2020 rover, I can assure you in the picture here on the left, this is the little plaque that contains 3 chips bolted onto the rover here. Those 3 chips contain over 10 million names that were submitted to be sent to Mars. So if you submitted your name to go to Mars, it's on one of those chips right there. After we assemble the spacecraft, we then, of course, put it into the fairing and then stack it onto the top of the rocket. And you can see the rocket here rolling out to the launch pad. And then the top right photo is the rocket sitting on the launch pad the evening before its launch on the morning of July 30. So here are some pictures taken from various angles of the launch itself. The picture at the bottom right is the one that I had in that previous slide. If you guys want any of these pictures, you can go to the website, which I'll show you later, and you can download these photos to your heart's content. But very successful launch, very exciting to see it on its way. As I mentioned, the next part of it will be the cruise. So it's currently cruising. It's about halfway to Mars now. So it left at the end of July. It will arrive in February of 2021. So it's about halfway there. So this picture that you see here is the trajectory that it will take. So here's Earth when it was launched and Mars when it was launched. This is its path to get to Mars, and so Mars will catch up with it. Earth will be here when the rover arrives, and Mars will be here. So you see these other little white ticks here that are labeled TCM. These are trajectory course maneuvers. These are corrections to the trajectory of the spacecraft as it travels on its way to Mars. So what we do is intentionally aim the spacecraft when we launch it to miss, just in case something goes, as we call it, off nominal. We don't want to crash land on Mars. And so we actually aim to miss and then correct the course a couple of times during its cruise. After we arrive at Mars, of course, then comes the hard part. We have to get down to the surface. So this little animated picture here that you see is the animation that was designed to show the delivery of the Curiosity spacecraft to the surface of Mars. So we will be using the exact same entry, descent, and landing system for landing Perseverance on surface. So it's the Mars Science Lab entry, descent, and landing system. We do have a couple of improvements in the guidance and the parachute, and so we should be able to shrink our what we call our landing ellipse, or the area where we expect to land, down from this 14 by 16 kilometer to about, they're now telling me about 6 by 8 kilometers. So really pinpoint, precise landing on Mars. And then once we get on the surface, then we have our surface mission. So the rover has been qualified to drive over 20 kilometers. We've seen our rovers do better than that in the past, and we're hopeful that we will, but it's the JPL engineers have given us a warranty for 20 kilometers. Everything is qualified to last 1.5 Mars years, which is about 3 Earth years. And again, our mission is to seek signs of past life and collect a set of samples. So this is what the rover itself looks like. So this is an animation. Again, you can find this online if you're interested in having a copy for yourself. What I've done here is taken the animation that has the instruments that are named on here. So you see there are 7 scientific instruments that we are sending to Mars on the rover. You'll also note that they're at the front of the vehicle here, this little round contraption here at the front. This is how the samples are going to be collected, and then how the sample tubes are going to be brought from inside the rover and put into the drill. And then once the sample tube is full, brought back into the interior of the rover. We'll check it out and make sure that it's okay. So what I want to do is go through the instrument suite relatively quickly. I will dwell a little bit more on the instruments that are more doing chemistry than the others. But in the interest of addressing all of the instruments, we'll go through each of them. So Mastcam-Z are our panoramic cameras mounted on the mast. The yellow parts are on the interior of the rover. This is just the electronics, and then this is a calibration target that it uses to make sure that it's doing its eye check. But these are the cameras that are mounted at the top that sort of give you the pictures that everyone likes to look at from the rovers. So the picture on the top left here is mounting Mastcam onto the mast. And then the picture on the bottom right, it's these 2 squarish looking cameras just under the masthead. So that's Mastcam-Z. You can see there's a pair of them, so we can do stereo imaging. They're also, they zoom in. So we'll be able to do 3 times zoom with these, which will give us even better pictures than were taken with a very similar instrument on a Curiosity rover. So this is Mount Sharp and Gale Crater taken with the Curiosity Mastcam. And so the Mastcam-Z, imagine this zoomed in 3 times, so you'll get a much better picture. These are just absolutely fantastic photos that Mastcam has been taking with Curiosity, and we'll have the same technology but with zoom and a little bit better resolution with Mastcam-Z. So just some more pictures that have been taken with Mastcam. The other part about Mastcam is that there are filter wheels, so we'll be able to do particular wavelengths of visible light. So we can do some filtering to sort of bring out different features and that sort of thing. Look for particular kinds of spectroscopic features, but it is not a spectrometer itself. The other fun thing that we can do is some astronomy. So this is pictures taken with Curiosity's Mastcam. The one on the left is Phobos, which is one of the moons of Mars eclipsing the sun. So that's a transit of Phobos across the face of the sun. The one on the right is Deimos, which is the smaller moon of Mars, also doing an eclipse across the sun. So we can do some astronomy, we'll take pictures of Earth, which they've done with Mastcam. So that's all fun. The next instrument I want to talk about is RIMFAX. RIMFAX is a ground penetrating radar. mounted underneath the radioisotope thermoelectric generator on the rear of the rover. So as the rover drives across the surface, it will be doing sounding. So it will be sending radar waves into the subsurface. And the idea, of course, is to get a view of what the structures, the geologic structures beneath the surface look like. So we'll be able to, detect changes in density, which is primarily what the radar will detect. So if there, for example, are any ice layers buried deep beneath the surface, we'll be able to find those, and we'll be able to see what the geologic structures look like, not just above the surface, but below the surface as well. So the frequency is, for those of you who care about radar, 150 to 1200 megahertz. The vertical resolution is about 15 to 30 centimeters. So we'll be able to see layers that are about 15 centimeters thick. It'll be able to go deeper than about 10 meters. And as it drives across the surface, it'll take a sounding every 10 centimeters. And so as it drives from, for example, left to right across this image, this is what we'll get. So it'll sound every 10 centimeters. Moving on to MEDA. So MEDA is our Mars Environmental Dynamics Analyzer, which essentially is the weather station. So this is one of the instruments that I was mentioning we'll be using not just for the scientific information of getting the weather, but also this will feed into climate models and understanding the atmosphere, so that when we send humans to the surface, we can give them a weather report, and we can also figure out what that will mean for humans as they try to land on the surface as well. So there will be 6 atmospheric parameters that MEDA will measure: wind speed and direction, pressure, relative humidity, air temperature, ground temperature, and then on the mounted on the deck will be a radiation sensor, which will measure discrete bands in ultraviolet, visible, and infrared. There's also a camera on there to look at the dust. So very interesting from a human exploration perspective. You may have seen those pictures, of course, of the Apollo astronauts when they came back from the moon. They were filthy. Their suits were covered in dust. It's probable that the dust on Mars may be toxic, may have some chemicals in there that wouldn't be particularly good for you if you ingested them. So we really want to understand the nature of the dust in terms of its stickiness, the electrostatic properties, all that kind of stuff. So we have a camera to investigate that. So the image that you see on the left is so these are the wind sensors. So they'll measure speed and direction, as I mentioned. These are the thermocouples to measure temperature, and the relative humidity sensor is on the back over there. So just to give you a sense that most of these are mounted on the mast, but there are a few pieces that are mounted on the deck. And then, of course, the electronics are inside the rover. All right, MOXIE is the other human-related instrument that we have. So this will be inside the interior of the rover. And as I mentioned, this is an in situ resource utilization experiment. So this is actually interesting chemically. So what it will do is take carbon dioxide, which is the main component in the Mars atmosphere. So it will take carbon dioxide, compress it, and then go through a solid oxide electrolysis process to create carbon monoxide and oxygen. And the oxygen, of course, will be hanging out there, and so it will combine with another oxygen and make O2. So the idea is to generate molecular oxygen out of Mars's atmosphere. So this, of course, will be very useful for astronauts when they get to the surface. If they can bring a machine like this with them, they won't have to worry about bringing oxygen with them that either they can breathe or that they can use as rocket fuel to get themselves back off the surface when it's time to leave. So this is a very interesting experiment that we'll be doing on the surface of Mars. Okay, let's get to the chemistry. So SuperCam is our first contestant here in the chemical arena. So SuperCam is called SuperCam because it does a lot of different things. So it's the next generation of instruments similar to the ChemCam instrument that we have on the Curiosity rover. So those of you who are familiar with ChemCam know that it does laser-induced breakdown spectroscopy to determine the chemical composition of the rocks at the surface. So it fires a laser, And then with the laser, it can do libs. It can also do, with SuperCam, a couple of other things that I'll talk about in just a second. This, of course, is mounted in the mast head, just above where mast cam Z is that we were talking about before. So the laser is mounted up there, and then the electronics are mounted in the body of the rover. So let's talk about what SuperCam can do. So there are three primary measurements that it can make. So we talked about libs already. So libs will be using a 1064 nanometer laser. Measurements, they're about 10% accurate on chemical composition. Part of that is related to the expectation from the calibration they did on Curiosity. They're working very hard on improving that calibration, so hopefully they'll be able to get better accuracy on SuperCam than they had on ChemCam. They will be able to do primarily major elements, but they'll also be able to do a few trace elements. If you're interested, again, I'll send you to the mission webpage at the end here, and you can look up all this information for yourselves. But primarily, again, this is laser-induced breakdown spectroscopy. So a plasma is created. By analyzing that plasma, we can get information on the chemical composition of the rocks. The second one, of course, is Raman. So there's a Raman spectrometer on SuperCam as well. The laser for that is 532 nanometers. So it's the same laser that LIBS uses. They just have a splitter to get a 532 or green laser, and they can do Raman measurements up to about 12 meters. The LIBS, they can do up to about 7 meters. So it is a standoff instrument, and so it's very rapid, which is one of the reasons we're really interested in this, because it can do it very fast. And then if we see something interesting, we can go study it in more detail. But this gives us a rapid reconnaissance way to do some measurements. So the Raman, again, is a 532 nanometer laser doing measurements up to about 12 meters. It does have time-resolved fluorescence capability, so we'll be able to gate out the fluorescence from the Raman signal. There is also a visible and infrared spectrometer. It's a point spectrometer. So you see on the picture on the bottom left here is reflectance as a function of wavelength and some of the minerals that we can detect using this spectrometer. So the Vis IR spectroscopy will be from 400 to 900 nanometers wavelength, and then there's a gap between 900 and 1.3. And then from 1.3 to 2.6, that should say microns, not millimeters. And the accuracy of the spectroscopy with the Vis-IR is 5 to 10% abundance for minerals. So this will be able to detect a lot of the more common rock forming elements that we see in the surface of Mars. So we'll get information about feldspars, pyroxenes, olivines, and then some really more interesting ones like phyllosilicates, carbonates, and sulfates that indicate evidence of aqueous activity. Now, these instruments will all be co-Bohr-sighted because we'll be using the same laser, and we'll be using a color imaging system. And so when we make all of these measurements, it will be essentially on the same spot on the rock. So we'll be able to do all of these measurements on the same spot on the rock, which is really great. The last thing that they'll be able to do with this is to do some atmospheric gases. So you can essentially point the laser at the sky and then do abundances of atmospheric gases. So we can detect oxygen, water, vapor, carbon dioxide, carbon monoxide, and ozone. To give you an idea, this is an image taken, a pair of images taken with the optics on the ChemCam on Curiosity. So this is in Gale Crater. So this is the Beachy target, which was done very early on in the mission. 1 gigawatt shot, 5 spot raster, 5 shots per spot. So what you see is that it makes these nice little holes, and that's due to the generation of the plasma with the laser. That plasma, of course, makes a little hole. It makes a little hole in the rock, and that plasma is studied spectroscopically to determine the chemical composition. So we'll be able to do this, again, really rapidly, and you can get some pretty good information. It will actually be able to bore into the rock a little bit. So remove the dust, for example, from the surface, and then look at the real composition of stuff that's not dust on the surface. So the picture on the bottom left here is what they expect to be able to see on a rock. So this, for example, is a basaltic rock. Again, co-bore sided, so you'll be able to do the Raman, the Vis-IR spectroscopy, and then the Lib spots. So very, very versatile instrument. The other fun thing we'll be able to do, because it uses a laser and makes these small holes, because it's a very small spot size. Once we collect the samples that we put into the sample tubes, we'll actually be able to shoot SuperCam into the hole that we created by taking a core sample to get some preliminary information about what's actually in the samples that we've collected. So that's also a really great thing that we'll be able to do. Again, just to nerd out a little bit here on some of the information that's come back from ChemCam, from the LIBS data, to give you an idea of some of the elemental compositions that they've been seeing with ChemCam, and then some of the information that they expect to be able to see through the visible and near infrared range as well. All right, so the next actually pair of instruments, we refer to them together, Sherlock and Watson. These are mounted out on the end of the arm on the turret. So we'll talk about these. We'll talk about Watson first, which is the wide angle topographic. I'm going to forget the rest of the acronym, but they invented that acronym, of course, to make Watson go with Sherlock. So Watson, of course, is essentially just a microscopic imager. So it will give us an up-close picture of what the materials look like at the surface of Mars. So for example, if we come across a nice sediment and we really want to know how well-rounded these grains are, how well-sorted the grains are, meaning if they're all the same size or not, which tells us a lot of information about the sedimentary environment that these sediments were deposited in, we can, of course, pick a spot and then get a nice close-up image of these things. So this very useful. You know, every geologist when he goes out in the field wants to have a nice hand lens to look at the textures of the rocks. So Perseverance has one. The other great thing that we can do, of course, with these cameras is take selfies. So because it's mounted out at the end of the arm, we can turn the camera back on the rover and take a series of pictures to make a selfie. So Perseverance already has a Twitter account, so you guys can go check it out if you want. Probably pretty bored right about now on its long cruise, but if you're interested, once she gets to the ground, then you can follow the Twitter feed. She'll probably be posting some selfies. All right, now the Sherlock instrument. Sherlock stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. So that's a big mouthful to essentially say it's a Raman instrument, and we'll be able to look for organic material and particular kinds of minerals. So this, unlike the Raman on SuperCam, this is an ultraviolet, a deep UV laser at 248.6 nanometers. The Raman scatter range is 800 to 4,000 inverse centimeters. It will be able to detect condensed carbon and aromatic compounds at 10 to the minus 6. Sorry, I missed the superscript there. Weight per weight at a spot size of about 100 microns. So very, very fine measurement and pretty good detection of organic compounds. It'll be able to do aliphatics down to about 10 to the minus 4. It will also be able to look at minerals, including ones that indicate aqueous chemistry. So things like carbonate, perchlorate, sulfate, phyllosilicate. So we'll be able to detect, you know, the sulfate bonds, and phyllosilicates, for those of you who don't know, are clay minerals. And so they have a silicon hydroxyl stretch that you can see. Carbonate, of course, is CO3. Perchlorate is ClO4. The organic compounds that it can see, the bonds it can see in organic compounds are carbon-hydrogen, carbon-nitrogen. carbon doubly bonded with oxygen, and carbon double bonded with carbon. So that's what Sherlock will be able to see. So you get to give you a sense, the picture here in the top center. Um, if you see this rock, for example, the really interesting part about this, of course, is the vein, the mineral vein that's running through this rock. And so you want to get an idea about whether whether this was created through aqueous processing, and maybe contains organic compounds. So you take a nice high resolution picture, scale bar of 1 millimeter here for reference, with Sherlock. And of course you can then you can superimpose your Raman signals on top of this. So what this picture indicates is that in this particular rock, you have primarily less mature organic matter, which lights up in the green here. So this is just superimposed Raman imaging onto the high resolution picture that we can take. Right, so apologies, the data that correspond to that image are on the right-hand side here. So you see crystalline SiO2, and then you see the G band in organics, which is less thermally mature, which is why this is lighting up green rather than the more mature stuff, which is mostly red over here. All right, and then I think this is the final instrument we're going to talk about. This is PIXL. So PIXL stands for Planetary Instrument for X-ray Lithochemistry. So it's an X-ray fluorescence instrument. So you see on the left-hand side, this is some data taken in the breadboard instrument, not the actual flight unit, but the breadboard as they were developing the instrument for flight, showing you some of the chemicals, the chemistry, the elements that they can detect in the rocks. So they can do 26 elements. So they can detect 26 different elements. For reference, the instruments that we have previously flown on rover missions to Mars are called APXS, or alpha particle X-ray spectrometers, which essentially do the same thing, but the APXS have a nuclear source, so that it's relatively limited in what it can do. And in fact, it can only detect and quantify 16 elements. PIXL will be able to do 26. For accuracy, it will be able to do major and minor elements down to about 0.5 weight%. It'll be able to detect trace elements in concentrations of up to tens of parts per million. So again, some of those are shown here in the inset box in the graph on the left: rubidium, strontium, yttrium, zirconium. Now it may be able to use because it has a rhodium filament, so it may be able to use the rhodium K-line ratio to get the abundances of some of the lighter elements that would be really interesting to get, like carbon, hydrogen, nitrogen, and oxygen. They're not guaranteeing me that, and it's not in their requirements to be able to do that, because as I'm sure you all know, doing light elements with X-ray fluorescence is a difficult, if not impossible kind of task. But they're going to try to be able to do those. No guarantees. Now, the really interesting thing about this, of course, is that unlike previous instruments like the APXS, which has a fairly large area, and so it essentially detects chemistry of whole rock rather than individual minerals or like a vein like we were looking at in that rock on Sherlock. The beam for PIXL will be 0.12 microns in diameter. So we will actually be able to do about 100 micron spot size to correlate the chemistry with the textures that we are seeing in the rock for the very first time on the surface of Mars. So that's very, very exciting that we'll be able to get down to those levels. The source, for those of you who care, is 28 kilovolt. It is a high voltage source, unlike the nuclear source, nuclear element source that we use with APXS. This will actually use electricity to generate a high voltage. So it'll get the electricity from the electricity provided by the rover through the RTG. It will be doing K and L lines to make those elemental identifications. And the other thing, of course, I should point out about Pixel is that the principal investigator of Pixel is a native of Australia, Abigail Allwood, who I think is from Queensland originally. But she's an Aussie, and she is the only female PI of an instrument that we have on the rover. So kudos to Abby. The other fun thing that we'll be able to do with this, of course, is elemental mapping. So we'll be able to look for trends in very fine scale in the rocks to identify particular minerals. So this one here, for example, is a chromium map. So chromium lights up here indicating the presence of a mineral called chromite. So again, the presence of these particular kinds of minerals and these elemental patterns tell us a lot about the potential for these particular areas to have hosted life on this sort of scale. So an example of that is what you see here in both the iron and sulfur maps of detrital pyrite. Pyrite is iron sulfide, a mineral which forms in generally oxidizing conditions. So again, this gives us a lot of information right up front about what was going on in these rocks. This one on the right-hand side in the bottom right is zircon. So zircon is a great mineral because we use that, we geologists use that to establish radiometric dates for rocks. So when you find zircon crystals in rocks, you can use that to get an age date on those rocks. So being able to find those right up front would be pretty spectacular, and may mean, yeah, we should collect that rock. So when we bring it back, we can get an age date on these rocks. The last one I want to mention here, of course, shows up in the manganese, calcium, and iron maps, which are various kinds of carbonate. So this is a vein of carbonate running through this rock, which again, finding these veins, and this would indicate that there was water flowing through this rock, depositing minerals that microorganisms are often associated with. So again, great to have this instrument and at such fine scales to be able to tell us a lot about what's going on. The other thing, of course, that we'll be able to do is combine the information from Pixel and Sherlock. They're both mounted out on the end of the arm on the turret. And so we can use both of these instruments to get a lot more information, build up a lot better picture of what's going on. So I talked about the elemental maps that Pixel made. Here is an example from a 3.4 billion year old fossil microbial mat from the Pilbara region in Western Australia, and images of what the Pixel and Sherlock data will look like for this. So again, this is a real fossil microbial mat collected in Western Australia, and this is the information you get from both Pixels showing silicon in green, calcium in blue, which there isn't a whole lot, iron in red, and then next to that, the Sherlock information showing presence of silicate minerals, carbonate minerals in blue, and then organic carbon. So you can tell that the carbonate minerals here, so this Sherlock, of course, is just looking at the bonds, the carbonate bonds, while Pixel doesn't actually show a whole lot of calcium. So this is probably a magnesium or iron-rich carbonate. So, and then of course there's organic carbon that you can see in layers, which would make sense. Again, detected from these 3.5 billion year old stromatolites from Western Australia. So this is the kind of information that these instruments will tell us about those materials at Mars. Okay, so that's it for the instruments, and I just have a few slides left, so hopefully I'm not running out of time here, but I want to go quickly over the rest of these just to give you a little bit more information about the mission. So some of you may have heard that we are flying a helicopter to Mars. So this on the bottom right-hand side is an image of the flight model of the what is now called Ingenuity helicopter that we are taking to Mars. So you can see it being mounted on the picture on the top here on the belly of the rover. So it is hitching a ride on the bottom of the Perseverance rover. The rover is flipped upside down in this picture, which is why you see people standing right side up here. It is mounted on the bottom of the rover. Once we arrive at Mars and find a suitable location for the test flights, we will lower the helicopter to the ground, detach it from its cables, and drive the rover away to a safe distance, and then do a series of test flights to demonstrate for the very first time, we hope, powered aerodynamic flight on Mars. So as you know, of course, the atmosphere on Mars is very, very thin. So flying something like a helicopter or an airplane will be challenging, especially a helicopter, because you need to get enough lift. And so the blades here, for reference, are 1.2 meters long. There are two of them stacked on top of one another, and they counter rotate, so we don't have to worry about the torque problems associated with a single blade as it spins. Powered by a solar panel that you see on the top here. The fuselage contains the batteries. There is a video camera mounted to the side. And then the landing legs. The entire thing weighs 1.8 kilograms. So it is very, very light, which we also hope will help as it tries to fly for the very first time on Mars as an aerodynamic vehicle. Now I mentioned that we'll be collecting these samples. So just to give you a sense for what this looks like, this on the left-hand side is a drawing of the coring drill. On the right of that is what the sample tubes actually look like. So the sample tube will fit inside here. So this top part will be down here at the bottom of the coring drill. So this will fit inside here. As the coring drill cores into the rock, it will the sample will be pushed into the tube. At the end of the tube, the interior of the tube, which you can't see here, is actually canted. So it will break off the core when it gets enough of the core into the tube. It will break off, and then this will then be taken back again through this contraption that you see them mounting on the top of the rover here, taken into the interior of the rover, where there will be a camera to look inside the tube to make sure it's in there, to assess how much material we got, and then it will be sealed up and then stored on the rover until we figure out exactly the strategy for retrieving them in the end. So how long we carry them around inside Mars 2020, whether we leave them in a pile on the surface for the next mission to come get. So the idea, of course, is that we will be then sending a mission to go collect them and bring them back to Earth for study here on Earth. So we are here, sample collection with the Mars 2020 rover. There will be a pair of missions that will launch no earlier than 2026, where we will have to land on the surface of Mars a vehicle, a launch vehicle, to get them back off the surface, along with what we call a fetch rover, a sample fetch rover, to go retrieve the samples and then load them into a container on the top of the rocket that will then blast off the surface of Mars into orbit. This container then will be collected by an orbiter, and then the orbiter will bring these back and then deposit them back onto Earth. So a little bit complicated in this architecture, but this is the plan. So send another mission to land on the surface with the return vehicle and the fetch rover. The fetch rover will go get them, bring them to the launch vehicle, which then launches off the surface, puts that into orbit for rendezvous with the orbiter for return back to Earth. So that's the plan. Of course, you can imagine doing a lot of things with these samples. Life detection, one of the primary things, looking for evidence that life might have left behind in the rocks. I mentioned geochronology to figure out how old these rocks are and whether that matches up with what we use as our crater counting. So the way we age date surfaces on Mars right now is we count the number of craters and how big they are, and we use that and the cratering record from the moon to get an idea about how old that surface is. So we don't have any actual, measured in the lab age dates. And the only way to get those is to bring samples back from Mars to Earth and measure those, find those zircons in those rocks and actually get an age date. So that will be fantastic. Of course, be able to understand a lot of the geologic history, carbon cycle, evolution of the lake, which we'll talk about in just a second. And then, of course, help us understand the Mars climate, because what happens with the climate, affects what happens with the rocks in terms of aqueous alteration, knowing when there were periods of liquid water at or near the surface of Mars, which also helps us understand a little bit about the atmosphere through time. So I keep saying, where are we going? I'm finally getting there. So the landing site for Mars 2020 is a place called Jezero Crater, or Jezero Crater, since it's a Serbian word. Jezero Crater is located here. This large blue patch is a large crater known as Isidis Basin, which was created by a large impact itself. Just on the edge of Isidis Basin is Jezero Crater. So you see the scale bar here, it's about 40 kilometers across. It has an inlet channel, so we see evidence of liquid water having gone into the channel and liquid water having flown out of the crater lake that existed inside Jezero Crater billions of years ago. A little bit, so some of the great geology that we think we see in Jezero Crater, I'll talk a little bit about this more in a minute, but we see a delta, so we'll see a better picture of that in just a second. Iron magnesium smectites, which are clay minerals, again indicative of aqueous activity on the surface of Mars. Lacustrine carbonates, so carbonate minerals that form at the edges of the lake. We'll look at those again in just a minute. As we all know, deltas, of course, and some carbonates are pretty good at preserving organic matter. So if there is any, this is a good place to go to look for it. Lots of great stratigraphy and sedimentology for us geologists to understand how everything formed here. Understanding, again, aqueous processes, atmospheric exchange of material for a very, very old area on Mars. So I mentioned the delta inside Jezero Crater. You know, here's a beautiful picture of it here on the right-hand side. You see the scale bar here. It's a few kilometers across. So here's the river channel coming in. As that river is running at relatively rapid speed, it hits a standing body of water, which was the lake inside the crater here, dumps out the material, forms this beautiful delta. So you see some remnants of pieces of the delta scattered here and there, so it's been eroding a little bit. We also see, of course, from orbit, we see evidence of these various kinds of minerals that I was talking about. The marginal carbonates here, which could have been a shoreline on the lake, and then various kinds of clay minerals, and then olivine, which of course is a primary mineral in igneous rocks. So we think this unit on the floor of the crater may actually be one, maybe igneous rocks that will help us get an age date for this entire area. Okay, so just to remind everybody, if you want to follow the Mars exploration program, all the great stuff we're doing, Curiosity rover still going, we have orbiters still going. We work with a lot of international partners, Europeans, the Japanese. I personally have started some collaborations with some of your faculty members there at University of New South Wales, Martin van Kranendonk in particular, who's been working with us on some things and has actually run a field trip with me out to the Pilbara to show the Mars 2020 science team members, a subset of them anyway, what they're up against when they go to Mars to look for things that look like the stromatolites that we were looking at in the Pilbara. So you can follow along, very easy, mars.nasa.gov, G-O-V. Perseverance, again, the mission website is mars.nasa.gov/Mars 2020. So very, very easy to find. As I was mentioning to your conveners at the beginning of the hour, all of the pictures that I showed you and many, many more and a lot of videos you can find. There's an entire multimedia section at the Perseverance website. So you can go there and find all these things, download the videos, watch them, download the pictures of the launch and stuff for your laptops and all kinds of stuff. So with that, I think I will end and thank you guys all again for your patience and for bearing with me for this hour.